All right. Hi, kids. I put on my growl fit today, plus my hat that scares off evil spirits, teach you about ideal gases. I'm wearing a noble gas shirt, but I'm not teaching about that. As you can see here, that's carbon dioxide bouncing around in the form of a solid. Dry ice. All right, so what we're going to do is we're going to take this dry ice. It's very cool. It's kind of frictionless because it kind of sits on a bed of air. Anyway, all right. What we're going to do is I'm going to teach you why we do the ideal gas law, PV equals nRT. N is the number of moles. So let's see how many moles of carbon dioxide there are in this piece of dry ice. Remember, don't touch dry ice with your bare hands. Put that on there, and that is too much. We'll need less than that. So we'll break off some. We need ballpark 3 grams. Are you getting that? You see that it's not 3 grams? How about now? 2.7. Are we good? Did you see that? Mm-hmm. Okay, good. So 2.7 grams. What we're going to do is take this dry ice, and we're going to make it turn back to gas by putting it into water and capturing the gas in this fancy vase. Can you see the vase? Zoom in on the vase. Mm. Zoom in. Closer. Closer. Too close. No. So as you can see, the gas is filling up the vase. While that happens, let's discuss science. All right. So we are using the ideal gas law. The ideal gas law is that PV equals nRT. N is the number of moles. We use 2.7 grams. I gotta stop. That's part of the reason I'm doing this is because of the panting. It's a lot of panting. I'll be okay. Okay. 2.7 grams of carbon dioxide. 2.7 grams of carbon dioxide. We need to convert that to moles. We're going to use the periodic table to go from grams to moles. Carbon is 12. Oxygen is 16. There's 2 of them, so 32 plus 12. 44 grams in 1 mole. Now, 2.7 divided by 44 is 0.061. 0.0613 moles of CO2. So, as you can see here, it's continuing to fill. Good work. And then, while that continues to fill, let's do the rest of this. The pressure in this room is, let's say, 1 atmosphere. We're going to say 1 atmosphere. We actually looked it up earlier, and it's like 1.01. So that's good enough, 1 atmosphere. Let's say we want to know what the volume of this vase is. We'll figure that out later, but it gives us something to look at. So V is our question mark. N is the 0.0613. Our R we're going to use, because we did this in atmospheres, is the R that has atmospheres in it. So that's 0.0821 liter atmosphere per mole Kelvin. Now, if we're in school still, you'd be doing this lab. Temperature. I know this is a 67 degree Fahrenheit basement. That translates to 19.4 degrees Celsius. We need this in Kelvin though, so we gotta add 273 to that for a total of 292.4. So now to solve for V, we need to multiply 0.0613 times the constant R 0.082 times the temperature, 292.4 Kelvin, and then divide by 1, which is basically like doing nothing. 0.0613 times 0.0821 times 292.4. Enter. 1.47. So we get 1.47 as our volume, and that's liters. Now, that's what we think is going to be in there. So as we come here, I might need to take that for a minute to really show what's happening here. All right, so as you can see here now, there's gas below the water level. See how the gas is in here and the water level's up here. So that means the pressure inside the tank is more than the pressure outside the tank. If I lift this up so that the water level is above or below the water level, so that the water level in the column is higher than the water level in the tank, then the water pressure outside is higher than what's in the tank. So water is being pushed into the tank by the atmosphere there. Water is being pushed out of the tank out of the column into the tank by the pressure inside. So if we line that up perfectly, then that is where it's at 1 atmosphere. So take that back. I think you need to flip it. I think we just went upside down. There we go. All right. So I need to mark that with a pen where that line is. And then what I'm going to do, well, good, it's close up there. Then what I'm going to do is release what gas is in there. All right, so that was full of carbon dioxide. Now we need to know, well, how much is that? We will find that out by filling this up with water and weighing that water, because water weighs 1 gram per mil. So according to our calculations, 1.47 liters equals 1,470 milliliters, which would then equal 1,470 grams. So in theory, if I fill this up to that line, it'll be 1,470 grams. Let's find out. First thing I need to do before I do that is tear this. So let's see what that weighs with no water in it. And then we're going to put water in it to that line. I know the suspense is killing you. There we go. And you will see that up to that line we have 1154, not 1470. So what we had is 1154 grams, which equals 1.15 liters, not 1.47. So why the difference? Why the difference, you say? Because this was not an ideal gas. This was carbon dioxide. And carbon dioxide, unlike an ideal gas, has some attraction to each other. And because it has some attraction to each other, I'm going to say it condensed some in there, right? If you had no attraction, think about it. If you have molecules with no attraction in here, then they wouldn't be pulled toward each other. They'd be bouncing around. If they had some attraction to each other, they'd be more pulled tight and thus take up a lower volume. That's what I'm saying. Also, some dissolved in the water. There's also water pressure involved. A lot of things that happen here. But if you just remember, the reason this happened is because they were attracted to each other and therefore took up less space, then I win. So, in conclusion, this was not an ideal gas, but it was a fun experiment to do with dry ice. Stay safe, kids. I'll do another lab when we need it.